All right, guys. So here in this chapter, we're going to talk about current, resistance, and simple circuits where you have combination of a battery and what we call a resistor. So in terms of then some of these things that we're going to talk about in this chapter, we mentioned in the previous chapter. So when there's a connection of the battery to some kind of device, I mentioned that there's electric field which makes the charges move. And in a way, we're going to kind of pick up from there and now kind of like elaborate. What do we mean by when there's electric field and charges are moving? And what does it technically do in our circuit? So we're going to see that we can look at it from the point of view of flow of charges, and which we call electric current, rather than electric field, even though this flow of charges in a some kind of conducting wire is due to the fact that there is electric field. So think like this. When we have some kind of a conducting wire, let's say a conducting wire, um, there are a lot of those what we call free charges that moving in a random direction. So they're randomly moving. And those free charges can be positive or can be negative. So we're going to see. So technically what we're doing here is we're going to be treating them as positive charges in this conductor. That means we're going to say that the charges that are kind of moving around freely are positive charges. In the reality, those are negative charges. The electrons are the one that are, free to move in a conductor. But let's assume it doesn't really matter. So some n number of charges freely moving in this conductor. And let's call this point A, which is one end of the conductor, and point B, which is the other end of the conductor. So if we connect this to a battery like this, so let's say this is some kind of battery source. Well, remember what happens, right? The battery right away generates or create an electric field, and this electric field goes from the positive terminal to negative terminal, and kind of goes like this. So that's the electric field, right? It goes through the conductor and then goes and comes back. Now, let's assume again, those are the charges, and let's assume that those are positive charges that are in the, you know, sort of like a segment of conductor that we're considering. So what happens when there's an electric field in that region from left to right, from A to B? Well, remember what happens to electric field, right? When you have a charge in the electric field, where there's a force acting on it, it's being pushed or pulled. And in this case, if those charges are positive, then they will be pushed in the direction of electric field. If those charges are negative, they're going to be pushed in the opposite direction of electric field. So then what we do, we take some kind of cross-sectional area A, and then we look at how many charges go through that area A as a function of time. So you can see, right? So then we can see that all of those charges now are collectively moving in one direction because they're being pushed due to this electric field. And the flow of those charges through that area A, right, area of this conductor, is then defined as electric current. So it's a rate of flow of charge through a surface. So we can calculate the average current, which we use capital I for that. So average current is delta Q delta T. That means number of charges going through that, through that area as a function of time. So delta Q delta T. We can also look at sort of like, let's say, instantaneous, which is then dq dt. So that's the equation for the electric current, or just simply current. So the current is nothing but flow of charges. Now there's what we call conventional current, and that is same direction that we would assume those free charges would move if they were positive. Remember, the idea here is that there is this, so let's say again, so if you look at this as a conductor, right, there has to be electric field in this direction for those charges, positive charges, to move in that direction. Collectively, they're all moving in the direction of the electric field. So If we assume that those charge carriers, right, the ones that are moving and giving us this, current, are positive charges, then that's the direction of the current. So conventional current has a direction same as the electric field. So that's why once we define what the current is, then we can say that, let's all, kind of like define the flow of charges, not in terms of, let's say, the electric field present in those wires, but that there's a current in those wires, which, right away tells you that if there's a current, that means there has to be an electric field to push and pull those charges. All right. So again, instantaneous current is basically the limit where delta T pushes zero. So delta Q delta T becomes dQ dt. The units are, it's Q over T technically, right? So coulomb per second. Coulomb per second, but we define that to be amps. And ampere or amps is the unit for the current. Generally, when we talk about current, the typical range is 10 to the negative 3, which is millicurrent or milliamps, so milliamps, to let's say few amps. Maybe, I don't know, let's say 20 amps or up to something like that. So this is a typical, value for the current that we would see. Can there be a microamp? Of course. Can there be a thousands of amps? Yes, if let's say if it's a lightning or something like that. But you know, most of the problems in everyday use of the current, it basically within that range. Now, the charges passing through the area could be positive or negative, or even both. As I mentioned, in terms of those what we call charge carriers, they can be positive or negative. In metal conductors, you can assume that they are always negative. The electrons are the ones that are moving. So let's say if this is the battery and it is connected to some kind of, segment of wire that we're considering, see, the current would be in the direction of electric field. This is plus, this is minus. So the current will be in this direction because that's going to be the direction of electric field, right? From the positive terminal all the way coming back to the negative terminal. So then the current will be in this direction. Like this, that's how we represent the current in the circuit. But in a way, what I have here is, if I know that the charge carriers were electrons, so let's say this is the electron, so electron, so they technically will be moving in the opposite direction. So this is then the flow of electron, right? This is the flow of electrons. So the electrons are kind of moving like this. But if I assume that the charge carriers are positive, then they're basically in the same direction as the current. If you can see right both, then the total, or the you can think like the current is a scalar quantity, by the way. This current is a scalar quantity, so it doesn't really have a direction. So this is just something that for convenience. So when there's positive and negative charges acting as a charge carriers, then the direction is defined, which one basically wins, right? Are there more positive charge carriers, or there are more negative charge carriers? So you can sort of like think of it like this, right? So if I give you I equals 2 amps, right? Well, if it's 2 amps, let's say it's clockwise. If negative 2 amps, then it's counterclockwise. So that's kind of like the idea. Now, as we have the electric field generated in those conductors because of the battery, electric field itself is pretty much moving at the speed of light. It's moving extremely fast through those conductors. Now, does it mean that those charge carriers also moving through the conductor with the same speed? Well, not exactly, and not even close, nowhere close to the speed of electric field. Those charges inside the conductor that, let's say, moving from, I don't know, point one to point two, let's assume that. So let's say you can say, right, there's a charge moving in this direction. So those charges are moving to the right from point one to point two. Why? Because there's probably an electric field in this direction. Well, electric field is basically pretty much instantaneous, going from positive and negative right in your circuit, because electric field moving at the speed of light. The charge carriers, when they move because of that, then we can define their speed to be what we call drift velocity, right, or drift speed, and then we can derive an equation in terms of how they are moving, inside this let's say, conductor. Okay. All right. So let's look at in terms of how we can rearrange a little bit of this equation. So think like this. So Q is a single charge going from point 1 to point 2. Well, there are, so let's say Q is a single charge, but there are n number of those charges, right? I mean, this region is filled with, 10 to the 20, 10 to the 30 number of charges. So let's say n number of charges. Then delta Q in the equation of the current, right, that delta Q is equals to n times Q. That means it's n number of Q charges, right, that are moving from one end to other end. Okay, so now n is the number of total number of charges. One thing we can do here is this. You can see, right, those charges are moving through this volume. Well, if I take the n number of charges and divide it by the volume, so this is volume, so n number of charges per volume, this is given as lowercase n. So you can see, right, this lowercase n is the number of charge carriers per unit volume. So we call that charge carriers per unit volume, sort of like a concentration. So the n, which is the concentration number, is equal to the total number of, these charges per volume. And let's look at what volume is. Volume is the area times, length, and let's take this to be the length, area times delta x. So then this becomes n over area times delta x. So this equation, now if I replace n, which can, if I rearrange, becomes lowercase n, which is the concentration, times a times delta x. So I end up with this equation. So delta Q equals, this is basically nothing but n, which is written like that, times Q. So the concentration number times area times delta x, where area delta x together is known as the volume of that, cylinder. All right, so that's the top part of the equation for the current. Remember, current equals delta Q over delta T. Now, what are we doing here? So this is known as a macroscopic equation for the current. So this is macroscopic. It's sort of like looking at the big picture. What we're going to do here is we're now looking at the microscopic. So microscopic equation for the current. That is why I'm going to be then replacing delta Q with this. So that means it's n number of charges. That means I'm already looking at sort of like single individual charges, but there are n number of those. So then the current, if I come back over here, so then the current, the delta Q part of the current, right? This one over here can already be written, let's say delta Q, right, can already be written as n times a times delta x times Q. Now, one other thing I do here is this. So you can see, right, those charges go from point 1 and point 2, they cover this displacement delta x, where delta x is a displacement is equals to v times t, right? It's same is equivalent to like writing as velocity times time. This is we call it drift velocity. That drift velocity is the velocity at which those charges are moving. That means displacement equals, speed times time. That's this thing, right? Speed is the distance over time. So distance equals speed times time. So that means over here, V, which is delta x over delta t, then I'm going to replace this delta x in this equation with delta x equals V drift times time. Then if I do that, here's my new equation. Here's my new equation. Concentration number, area, drift speed, I mean, in this case, it's speed because it's a current. Then times the time interval times Q. So then when I divide this by delta t, right? So then delta Q by delta t, this delta t cancels out. And then this is then microscopic equation for the average current in your circuit. So this is basically, you have in a way two equations, right? Macroscopic and microscopic. And this is how those two are equivalent. But the second equation, right, the microscopic equation includes information about, sort of like a charge carrier, right? Single charge, how fast they're moving, through which area they're moving, and what is the concentration number for those. Okay. So, and if you, let's say, use this equation and calculate the drift speed, you will see, for example, how fast they're moving. There are, examples that, we will be able to see for that. But that's kind of what we have. Now, does it mean, let's say, remember what I said, right? If there is electric field which is moving at the speed of light, that those charges also moving at the speed of light? Remember I said no. That number is nowhere near. That's because, let's say there's a electric field to the left and the charge carriers are negative charges, which means that they're going to be moving in the opposite direction. So what we have here is there, you can see sort of like, let's say how they're moving, right? So like this, zigzag, right? Because there are a lot of those. They're colliding constantly with one another. They're basically barely technically moving. Average drift speed is few millimeters per second, few centimeters per second. So they're barely, moving compared to the electric field, which is technically, again, is moving at the speed of light. All right. So when the potential difference is applied, can I summarize this? An electric field is established in the conductor. Electric field exerts a force on the electrons. The force accelerates the electrons and produces a current. Okay, that means the current is nothing but a flow of electrons. That's in a conductor. So the motion of electrons due to the electric force is superimposed on their random motion to provide an average velocity whose magnitude is the drift speed. The changes in the electric field that drives the free electrons travel through the conductor with the speed near that of light. This is electric field, right? Moving at the speed near that of light. So this is why the effect of flipping a switch is effectively instantaneous. Well, then if the charges are moving at, at barely, drift speed, right? So then again, how is the light is on as soon as you flip in the switch? Well, because going from where this is the let's say the switch is to where the light bulb is, right? Let's say, well, you have wires. Yes, electron from here not going to be able to go to the other end, you know, as fast as the electric field. But think like this: all this region is filled with those electrons, and as soon as you flipping the switch, there's an electric field that goes like this, basically instantaneous. And it doesn't just affect this charge; it affects all of them. So that means it affects charges that are right next to the switch and charges right next to the light bulb. So then this, as soon as you turn on the switch, this guy enters and then your light is on. All right. So when electrons make collisions with metal atoms during their motion, they transfer energy to the atoms. This causes an increase in the vibrational energy of the atoms and a corresponding increase in the temperature of the conductor. Right. So this is very important information. That means if you have a wire and there's a current running through the wire, well, because of those collisions, and there are tons of collisions, as small as those you know electrons are, right? Because there's a large number of them and they're colliding, those wires actually get really hot. So that's why a lot of times when there's a fire in the household, right, that's due to the fact that the current in some wire can become extremely high, and then the current is high. Well, current high means that those electrons moving fast. As they're moving fast, or there's basically the large concentration of those moving. So those collisions can really heat up the wire through which they're moving, and that wire can heat up so much that it can basically start fire. Okay, so that's why there are circuit breakers and things like that, right, in our houses, so for that not to happen. That means as soon as you have several things, you know um, let's say, like let's say turn on, right, so like devices or things like that at the same time in your house, you're using up a lot of current, and that can technically be dangerous. So that's why when you maybe use 3 or 4 or 5 things at the same time, sometimes your circuit breaker basically helps you prevent any type of fire. So your circuit breaks, and that prevents a fire. Now, what type of energy do you, let's say, usually have? Well, there are generally kinetic energy, because the charges are moving, and there is a potential energy. And usually the energy that goes to converted to heat are the potential energy of those particles. because the kinetic energy more or less is unchanged. Because once the charges are moving, they're pretty much moving with the same speed. So that means they have the same kinetic energy the entire time. Potential energy, on the other hand, always decreases by the time they get to the negative terminal. That means when they complete one cycle, they basically use up all of their potential energy. Luckily for us, the battery can provide them with a new potential energy, new amount of potential energy, and then they can go around in a circuit again by using that potential energy that they gain from the battery to operate other things. Because for example, light bulb operates by basically those collisions. The light that you see is actually a thermal energy. All those collisions generate thermal energy, and what you see here, you see the light because of the that's the thermal energy, thermal heat. Okay, so that's why the light bulb are very very hot when it's operating. All right, we're going to be talking about that later on when we look at the let's say the circuit diagrams, but that's kind of like the big picture. Okay, so the energy is transformed by work done within the system by the field and the electrons to kinetic energy of the electrons. When electrons strike the metal atoms, some of the kinetic energy is transferred to the atoms, which adds to the internal energy of the system. Okay, so that's why the atoms in a filament of the light bulb collides with the charge carrier electrons, and the energy that that transferred to the filament atoms then basically makes them glow, and that glowing is in a visible spectrum, so we can see that. Okay, so there are a lot of collision around you right now that make objects glow. You are glowing, the chair and the table in front of you are glowing, but they are glowing at the infrared. We can't see them. Our eyes are not equipped to see those type of let's say heat signatures. But we do have equipment that can detect infrared and things like that, right? So those are the equipment that that have a much larger visible spectrum, so we can detect that. That's ultraviolet, infrared, or things like that. Those are basically object radiating energy at a different let's say frequency that our eyes cannot interpret. Now, one thing we have, I mentioned already, is that current is a scalar quantity. That means if I have a conductor like this, and I have, like, let's say that conductor connected to the battery like that. So let's call this point A, let's call this point B. Well, what I have here is, since this is the positive terminal, this is the negative terminal, then the conventional current will be in this direction, from positive going through the conductor, from A to B, like this, right? So that's the direction of the current. Again, current is a scalar quantity. So this current here is a scalar quantity. Okay. But we just give it sort of, for convenience, we give it a direction. But there is another quantity, J, which is current density, that we can use, which is actually a vector quantity. That means I can look at this cross-sectional area A, and I can say that current through that cross-sectional area A is defined as current density. So remember, the current was NQVD times A. So then if you divide this by A's cancel out, and you have just NQVD. And this is the magnitude of the current density. The current density is technically a vector, and it equals to NQVD. VD this time is the velocity, drift velocity, not the speed. In the current equation, that's the speed because it's a scalar quantity. In the current density equation, that's the velocity. So that's why if the carriers are moving to the right, then current is in current density in the same direction. Okay. Now, technically, what you have is this: the current density. Well, not necessarily it's always in the direction of the velocity. What you have to think of it like this: it's always in the direction of the electric field. Because if this is, let's say, if the charge carrier is positive charge, they are moving in the direction of the velocity, in the direction of electric field. VD is basically in the direction of electric field, which is going to be from A to B. So then when I do J, which is equals to N, then Q is positive, and then VD, so VD is in the same direction. Let's say VD is positive, Q is positive, so J is also positive. Positive means basically, let's say, to the right. But if the charge carriers are electrons, what I have here is this. If it's electron, they are moving to the left. VD is basically to the left. So, but remember, electric field is still, to the right. Well, but this time the Q is negative. So then if VD is negative, they cancel, and you still have the same J has the same direction as electric field. That means J has the same direction as electric field, always. And it's a vector, in the same direction as the electric field. All right, so let's look at an example here. An electron beam emerging from a certain high energy electron accelerator has a circular cross section of radius 1 millimeter. The beam current is 8 milliamps. Find the current density in the beam, assuming it is uniform throughout. All right, so let's look at that first. So the beam current is 8 microamps, and we want to find the current density in the beam, assuming it's uniform throughout. All right, so remember, current density is this quantity J, and we can find that from current divided by amps. Sorry, to current divided by, you know, the area. So the current here is 8 times 10 to the negative 6 amps. Area, well, it's a circular, cross section. That means it's pi times r square. Well, r is the radius, so it's 0.001 meter square. And we can find this basically by just dividing one with the other. So doing this calculation, we're going to get 2.55 amps per meter square. Again, this is in meters. So we get 2.55 amp per meter square. Part B says, what is the speed of the electrons? Well, the speed of the electrons is so close to the speed of light that their speed can be taken as 300 megameter per second with negligible error. Okay. So find the electron density in the beam. Well, this is not the current in some kind of conductor, right? This is basically an electron beam in a energy accelerator. So this is a completely different thing. So don't confuse this with the drift velocity of electrons in a metal conductor. So for part B here we have, so the speed is equals to 300 megameter per second. So that means it's roughly 3 times 10 to the 8 meters per second, which is, nearly speed of light. So nearly speed of light. So we can actually have electrons or protons accelerating at 0.999 speed of light. So we can round it here and say roughly, 3 times 10 to 8 meter per second, which with a negligible error. Okay. So find the electron density of the beam. Well, we also know that J is equals to NQ times V, right? NQ times V. So rearranging this to solve for N, that's what we have for the electron density. That's N, right? Concentration number, right? That we call that density number. So this is then J over, Q times V. All right. So the J we just calculated, it's 2.55 amps per meter square, and then divided by it's an electron, so 1.6 times 10 to the negative 19, and then the speed is basically 3 times 10 to 8 meters per second. Okay. So just go to the next page. All right. So let's say what we have here is the N is equals to 5.31 times 10 to the 10 meters to the negative 3, which is basically the particles, right, per cubic meters, because it's a number of particles per volume, right? So that's the units for this concentration. All right, so part C. Let's see what was the question. It says, over what time interval does Avogadro's number of electrons emerge from the accelerator? All right. So we are basically given some specific number of molecules, and Avogadro number Hopefully you guys remember your Avogadro number. It is 6.02 times 10 to the 23 particles, or in this case, basically electrons, right? So we put like as electrons. So electrons like that. All right, so we have this number, right? Um, well, think like this. If you remember, right, I said that Q, total amount of charge, right, or delta Q is equals to n number of, charges and or n number of electrons. So now we have Avogadro number of electrons. That means that's basically just, Na times E. So basically we are given in terms of, by the way, this is like, let's say Na is this many electrons, and this equation is actually Avogadro number time the charge of the electron. Okay, because what I have here is current is then delta Q over delta T. So if I rearrange this, then delta T here is equals to delta Q over the current. Well, the delta Q is Avogadro number of electrons, and current here we were given as 8 times 10 to the negative 6 amps. All right, so then delta T will be equals to 6.02 times 10 to the 23. That's the Avogadro number. 1.6 times 10 to the negative 19 coulomb. That's the electron charge. Then divided by the current, 10 to the negative 6 amps. We calculate 1.2 times 10 to the 10 seconds. All right, so it doesn't tell you much, but if we convert it to years, 382 years. All right, that means you can see, right, it will gonna take 382 years in order for Avogadro number of molecules go through that some area A of interest. That means, as charges are moving, if you want to sit down and calculate or count how many electrons moving and count until you get this number, you better be able to live 382 years, because it's going to take that long. All right, so then here's sort of like important thing about let's say important concept that we're going to be learning in this chapter, and that's the concept of resistance. And basically a circuit element or a device is called a resistor. So in a way, think of it like this. So if you have this conducting segment of wire, right, and let's say if you connect this to a battery, as I basically we've been doing right now, well, as I mentioned, right, there's going to be a current going through this. So here's a current going from positive terminal, and then this is, let's say, point B. Let's say this is point A. Okay, doesn't really matter, B or A, where you're going. But the idea is that there's going to be current in this direction. You can see, right, there's a current like this from B to A throughout that conductor, because there's electric field, right, from B to A in that conductor. What the electric field will do, push the charge carriers inside that conductor. That electric field is responsible for pushing the charge carriers inside the conductor. Now, again, electrons will be pushed in the opposite direction of electric field from A to B. If you assume that there's a positive charge carriers, they're going to be pushed from B to A. It doesn't really matter. So we can right now just agree that let's assume that charge carriers are positive, and current is the sort of like flow of charges. And if we can assume that conventional current represents what would have been the direction of the positive charge flow. So we're going to assume and agree to that. That means what I have here is this. There's going to be a bunch of charges moving from point B to point A throughout that conductor. Okay. Now, from the conductor's point of view, right, that segment of wire, its own molecules, right, its own atoms, then can try to resist the charge of the charge carriers flow. So then what the segment of wire can do, can create a resistance inside the conductor, try to resist to the flow of charges. In a way, try to basically limit how much current you can have, because current is basically the flow of charges. So this device is known as a resistor. Then the resistor is a device that can resist the flow of charges. And they are very important because they can be used as a limiting factor for the charge flow. Because remember, what I said is that when you have a large amount of charge flow or high current, it can be dangerous because it can heat up the metal wires very much and it can cause fire. So, but if your wire has a really large resistance, then that resistance can limit how much current it goes through the wire. So, for example, if you have a battery voltage of, let's say, 20 volts, okay. Now, this battery voltage, remember, so is basically responsible for giving us, you know, this electric field. We know that already, right? So but since positive terminal connected to point B will have the same potential as positive terminal. Since negative terminal connected to point A will have the same potential as the negative terminal of the battery. That means there's going to be a potential difference, right, between A and B. So there's a potential difference between those two ends of the conductor. Well, that creates this electric field because there's a non-zero potential difference between them. And that electric field will then push the charges. Now, how effective it will be will also be determined by the amount of resistance the conductor can provide to the flow of charges. Okay. So, taking the potential difference between the ends of the conductor and divided by the flow rate, which is the current, we can determine the resistance that this conductor can provide. R is equals to this ratio of delta V over I is defined as the resistance of the conductor. Okay, and the conductor then can be called as a resistor, which is like sort of like a capacitor, capacitance, resistor, and the resistance is its value. Okay, so the units are volt per amps, or V over A, but one V over A is defined as 1 ohm, and ohm is a resistance unit, and basically it's Greek, capital Greek omega. So we use resistance to pretty much control how much current we can have in our circuit. Okay, so it's a very important device, very important role plays in our circuit, and we're going to be basically using this entire next several chapters, right? We're going to see that especially when we have DC circuits, we have AC circuits, resistance is a very important part of that. All right, so this equation is also pretty much just different rearranged version of what we call Ohm's law. So you can see, right, resistance and Ohm's law. So Ohm, actual scientists who, even though the unit you can see, right, ohms, for the resistance is actually, after him. He did a lot of contribution to this, our understanding of the voltage, current, resistance, let's say, um, relationship. And this equation basically is what we call Ohm's law. It relates resistance in the conducting wire to the potential difference across it and the current going through that. So a lot of times this equation is basically written as V equals R times I, where R here is basically a proportionality factor. But we'll see that in a minute. All right. So think about comparing current, voltage, and resistance to the flow of water in a river. Kind of like analogy. As water flows downhill in a river of constant width and depth, the rate of flow of water, which is sort of like analogous to current, will depend on a number of things. And these are sort of like same factor as the resistance in a conductor. So it depends on the total vertical distance through which the water drops between 2 points. Well, this is, you can think of like, let's say the vertical distance, right? So let's say if you have an incline like this and water goes through that, will be different flow rate than if, let's say, you have an incline like that. Like steeper it is, faster the water will, go down. This can be analogous to then potential difference between the two ends of the conductor, because the current is directly proportional to the potential difference. Higher the potential difference, larger the current value. But then the water also depends on the width and depth, as well as the effect of rocks and the riverbank and other obstructions. That means what prevents, what resists the flow of the water? Well, let's say the rocks, riverbank, and other things. Well, then that is analogous because those things, right, will slow down the water. So analogous to that is then the resistance, which is then you can say right, current is proportional to 1 over r. That means more obstruction, lower the value of the current, less flow rate, thing like that. So that's why this current in a way equals to the potential difference, which is it's directly proportional to, but then inversely proportional to resistance. So that's why resistor in the circuit is a device that can limit how much current you can have. Even if you have, let's say, maybe you have a fixed, let's say potential difference, but putting a resistor can decrease the amount of current in your circuit. Or it can increase if you, let's say, remove the resistance. All right, so the electric current in a uniform conductor depends on applied voltage, and the resistance of the conductor is caused by collision of the electrons with atoms in the conductor. So this is basically the Ohm law in a nutshell. So Ohm's law states that for many materials, the resistance is constant over a wide range of applied voltages. And we call that ohmic resistors. So most metals obey Ohm's law, which means that this equation, current equals delta V over R. This equation is what we call Ohm's law. Okay. And most of the metals, right, we assume that R is more or less constant. Okay, more or less constant. Okay. And let's say if you rearrange this equation, for example, and you have then delta V is equals to resistance times current, it means if I'm plotting delta V as a versus current, then I should get like a straight line like that. This is, we're going to talk about that. This is known as an ohmic material, and which means that R is constant, right? So it's a linear proportionality between delta V and I. So you can see the few graphs over here. You can also plot I over delta V. In that case, the slope is 1 over R. So, and we're going to have a lab actually, identifying this. So we should be able to see that from the experiment. So the materials that do not obey Ohm's law are said to be non-ohmic. Okay, so here's the thing: we will be working with mostly ohmic material. You can see, right, the non-ohmic materials are um, that generally a little bit more difficult to work with because you can see that it's a nonlinear relationship, right? So and some of those materials are let's say beyond the scope of this class. But you can think of, like, let's say they are materials, so and you will be eventually studying those type of materials as well. All right. So most of the things that we're going to be looking at basically here. So for the ohmic device, the resistance is constant over a wide range of voltages. The relationship between current and voltage is linear. The slope is related to the resistance. That means once you find the slope of this graph, you can find the resistance from that. Okay. And non-ohmic materials then in a way depend on type of device that you're using. You can have like a diode, or maybe like a filament of a lamp that basically changes resistance because you have a high temperature, or variation in temperature and things like that. So, but those are the things that we might kind of look at it, but not necessarily cover in great detail. All right. So here's how we represent the resistor as a device in a circuit. Okay. So let's say this will be point A, one end, point B at the other end. So then delta V, the voltage for the resistor, basically what is the potential difference between these points A and B? So VAB is just basically what we call delta V, right? It's the voltage of the resistor. So what is the potential difference between two ends of the resistor? And according to Ohm's law, it's a product of the current and resistance. Okay, so the delta V equals I times R. Okay. Now, this resistance value getting from delta V and I is very similar to the capacitance value from Q over V. Remember what I said for this, for this capacitance equation. You double V, you double Q, and that ratio remains the same. You make voltage 10 times, you move 10 times the current, the charges, and the ratio is still the same. Well, same thing is here. Let's say you have 10-volt battery connected to the resistor. So let's say then the current that, let's say you have is, let's say, 2 amps. So then this is going to give you like 5 ohm resistance. Well, I make this 10 times more. then does it, let's say, will if the voltage now is 100 volts instead of, let's say, 10 volts, will that change the resistance? No, because then it will, since you're making the voltage 10 times, well, it generates 10 times stronger electric field and moves 10 times, more, let's say, the rate of charges. So current now is 20, and then you get same 5 ohms. That means this ratio never really, changes the value of the resistance. It will help you to calculate the value of resistance, but doesn't, in any way change the value of resistance. Because just like the capacitor, remember the parallel plate capacitor, so you can find the capacitance for Q over V, but that's about it. No value of Q or V or will ever change the capacitance value. But capacitance was epsilon naught A over D, and you could change it from the geometry of the capacitor. Well, same thing here. Resistance is a quantity, or is a property of this metal wire. Let's say that segment of metal wire that only can be changed by changing the properties, geometric properties of the wire. So you have this cross-sectional area A, and then the length of this conductor. So then the resistance of the resistor will change if you change those geometric properties. Make it longer, make it shorter, make it wider, make it narrower, right? Those things will be, let's say, affected. That means going from R, so the resistance is directly proportional to length. That means longer it is, stronger the resistance. But, it's inversely proportional to area. That means wider it is, right? More charges will flow, so the resistance technically decreases. Going from proportionality sign to equal sign, we introduce a constant, and that constant is then resistivity of that material, which is different from the resistance of the material. So think like this: resistance represents information about this very specific resistor. So let's say, let's say it's a copper resistor, right? So it's a copper wire. Okay. Well, I understand it's a copper wire, but you can have different resistors that are also copper wire. We can have something like this, something maybe like that, another one maybe like this, right? Different length, size, and things like that. Rho, which is known as the resistivity for the copper wire, right? Because it's a copper, resistivity is the same regardless the size of the resistor device. Okay, so rho, for example, for copper, I should have a value for that. I might have a table, but it's a 0. Let me see if I have a table for that. There you go. No, not that. All right, so we'll come back to that. So then let's say the resistivity of the copper wire is the same, regardless of what type of copper device I have. But the resistance is very specific to, let's say, this particular device. So it depends on its length and its area, right? So that means if it's copper, so this is then resistivity for copper, then times specifically this length of this resistor over the area of that resistor. So that's why resistivity is always the same as long as, let's say, it's a copper. Resistance changes, so you can calculate that. All right, so the resistivity generally has a unit of, ohms times meters. That's the unit for the resistivity. All right, so again, here's an equation, right, for the um, resistance from its geometric properties. You have two things. You have rho is the resistivity, and then you have sigma, which is known as a conductivity. And resistivity is 1 over conductivity, or vice versa. So that's why you can either write this as rho L over A, or 1 over sigma L over sigma A. That means this represents in terms of conductivity, rho represents resistivity. So you can say, right, an ideal perfect conductor would have 0 resistivity or infinite amount of conductivity. An ideal insulator would have an infinite resistivity or no conductivity. Okay, so two common types of resistor: composition resistor containing carbon, or wire wound resistor consists of coil of wire. So those are the type of resistors we'll be dealing with. We don't necessarily looking at composition unless it's experimental lab where we can see sort of like a difference between them. But in this case, let's say you're going to be mostly given in terms of type of material it is, length, area, and things like that. So you can then calculate the resistance. All right. Another thing for convenience, what we do here is when the resistors are manufactured, they are color coded. And color code allow us to find the resistance value without, let's say, us, let's say directly measuring that. So those color codes allow us to, let's say here's a resistor. So it has, one color, second one, third one, and another one right here, which is basically ends up being what we call tolerance. So there are going to be three colors, right? So let's say 1, 2, and 3. So then you can look at the first one. So let's say the first one here is, I don't know, let's say orange. So let's say this one is orange. Let's see if I have orange. Let's say this one is orange. So then if this is orange, I can see that orange is 3. So I write as 3. Let's say then second one, for example, is green. Let's see. Then I look at green. Green is 5. So then I can write 3, 5. So 3 because it's orange. The first one is 3 because it's orange. Second one is 5 because it's green. And the third one is generally then becomes what we call a multiplier. So let's say, for example, it's, I don't know, let's say red. Okay. Then I can see red multiplier is 10 to the 2. So I do 35 times 10 to the 2. Okay. So that's basically the resistance value. So 35 times 10 to the 2, which is like 3,500 ohms. Okay. So that's kind of like what we have. And then last one, if this can either be gold, silver, or colorless. So if it's colorless, then it's 20% tolerance. That means what is the quality of this resistor? Let's say over time, how, let's say, reliable its value is. So you can see, right? Colorless means that it's not really that great. So it can change its value by 20% over time. Silver is 10%, gold is 5%. That means, gold is probably the standard, right? The best manufacturer, the resistors. So they, if it's this value in 5 years, 10 years, maybe like, let's say 5% difference, but not by much. All right. So again, here's an example, different one over here. So you can see, right, the first one here is yellow, gold. So you look at yellow is 4. Second one is black. Well, you look at, oh, sorry guys, we go actually from here. Um, so this is yellow, then violet. So that means 4, violet 7, and then this is black, which is the multiplier. So it's 10 to the, sorry, it's 10 square. Or let me see, the black is what? So the black is 1, just 10 to the 0. Oh, this 0 should have been a subscript. So 10 to the 0, which is basically 1. So it becomes 47 ohms. That means that's the resistance of that resistor. And since this is gold, that means plus minus 5% or 2 ohms. That's the tolerance. So you can say it's 47 plus minus 2 ohms. So like, let's say it's tolerant or it's uncertainty. All right. So in this equation, then we show how we recognize that resistance as the wires get, get hot because of those collisions, the resistance can actually change and resistivity of the material can change. And then when we look at the resistivity of the material because of those collisions and things like that, we have then the equation when it says this is the resistivity at the room temperature. So let's say 20 degrees Celsius. But then as the temperature increases, then resistivity equals basically this equation over here is resistivity times the quantity 1 plus alpha times delta T, where alpha is the temperature coefficient of resistivity. Okay, so just another constant representing temperature, coefficient of resistivity. Same thing, we can write it in terms of technically the resistor. That means we have same format equation for the resistor. That means resistor at some temperature is equals to the resistor at the room temperature, then 1 times 1 plus alpha coefficient, then times delta T. So If delta T, think like this, it becomes like this. So R is equals to R plus R naught plus R naught alpha delta T. So in a way, this is what you get. So if the temperature delta T is positive, that means you increasing temperature, this term is positive and adds to the original value. So your resistance increases. If delta T is negative, that means you're decreasing temperature relative to the room temperature, then this term is negative. Then you're then subtracting and your resistance pretty much decreases. So you have those increasing, decreasing things. Okay. So you also have superconductors. So superconductors are metals and compounds whose resistance go to zero below a certain temperature Tc. There are a lot of applications, lot of research on trying to make the best possible superconductors and things like that. Because the idea here is this: superconductors mean that basically very low or almost negligible resistance, which means that there is no resistance to the current. So once you kind of like give it like a driving, like let's say voltage, your system can then operate without necessarily losing its energy too much. So, but the worst thing or the bad thing about that is look at the temperature in Kelvin is 4, 4.1, 4.3. This has to be done in a very low temperature, close to the absolute zero. So that's why it's, let's say, you're not going to see something like this in in everyday appliances and things like that. And this is how the graph of the resistance as a function of time, temperature. So it decreases, decreases, decreases. At some point, it jumps to basically completely zero resistance. Okay. All right. So the value of Tc is sensitive to chemical composition, pressure, crystalline structure. That's basically that critical temperature at which the resistance goes to zero. Once a current is set up in the superconductor, it persists without any applied potential difference. That means all you need is just a little bit of, let's say a push, right? And then they can, go around in a circuit, like let's say, without necessarily losing their energy and things like that. So there's no resistance, and the current, will not dissipate, charges will not dissipate their potential energy. All right, so let's look at another example here. So an aluminum wire with a diameter of 0.1 millimeter has a uniform electric field of 0.2 volts per meter imposed along its entire length. The temperature of the wire is 5 degrees Celsius. Assuming the temperature of the wire um, is 50 degrees Celsius. Well, repeating. All right, so assume one free electron per atom. Okay. Use the information from table, to determine the resistivity of aluminum at this temperature. So this is basically table, one of the tables in the book. All right, so what is the current density of the wire? What is the total current of the wire in the wire? And what is the drift speed of the conduction electrons? And what potential difference must exist between the ends of a 2-meter long length of wire to produce the stated electric field? All right, so there are a lot of things we have to, look in this particular example. So let's look at in terms of what we're given. So we're given that diameter is 0.1 millimeter. All right, so let's look at part A. Use the information to determine resistivity of aluminum at this temperature. Well, equation when there's a change in temperature, in terms of, let's say, I think there's something missing here. So let's assume this. So we start with the 20 degrees Celsius room temperature, and then it goes into 50 degrees Celsius. That means it increases the temperature by 30 degrees. So then resistivity equals resistivity at the room temperature, 1 plus alpha times T, let's say T2 minus T1. Okay. So using the information, let's say from the table, where we can find the resistivity of aluminum wire. So where that value is 2.8 times 10 to the negative 8 ohms times meters, then 1 plus, then alpha, well, alpha also basically depends on type of material. So let's say if this is aluminum, it's 3.9 times 10 to the negative 3 degree Celsius to the negative 1, because in a way, what it does, it cancels the units for the temperature. And times 30-degree Kelvin or Celsius, doesn't matter because it's a delta T. So let's say Celsius. All right, so this is basically our equation to calculate the resistivity. We can see then the resistivity after the temperature increased by 30 degrees will be 3.15 times 10 to the negative 8 ohms times meters. So that's basically part A. Increase in temperature increases the resistivity, which also then can increase resistance, of course. Again, because the resistivity increases, it can also increase the resistance. Part B says, what is the current density in the wire? Well, current density, we have an equation where the current density is equals to current per area. So current per area. Now, in terms of then what we can do from here, so in this equation, we don't have the current. We're not given current anywhere in the problem. But we know that using the Ohm's law, current is related to the potential difference divided by the resistance. Okay. Now, potential difference is electric field times length of the conductor, right? E times L, E times D or E times L. Resistance is resistivity times area, then divided by L. Okay. So if I put this together, I can see that here what I have, okay, sorry, I made a mistake there, is resistivity L over A. So then I can cancel the length and then have an equation where it's E over rho times area. So that's the equation for the current, getting from the Ohm's law in terms of the electric field. Okay. So since we're given the electric field, which is 0.2 volts per meter, and we just calculated the rho, then I can say, all right, so then J, which is current density, equals current over the area, and the current is electric field over resistivity times area, then divided by area, area cancels out. And this is just equals electric field over the resistivity. And current density, electric field, 0.2 volts per meter, divided by resistivity over 3.15 10 to the negative 8 ohms meters. Then we can calculate this to be 6.35 times 10 to the 6 amps per meter square. Or technically 6.35, 10 to the 6 is mega amps per meter square. All right. Let's look at then part C. It says, what is the total current in the wire? Well, now that I have current density, which I calculated without technically needing the current, and look at, I can use this equation technically also to calculate the current, but it's easier to just use this equation to calculate the current, where I, in part B, I eliminated current technically. But the current is equals to current density times area. So 6.35 times 10 to the 6 amps per meter square, then times area. Okay. Area is just pi r square. Well, I'm given the diameter, and just half of that is basically then the current, the area. So pi times, half of that. So zero point 0.5 times 10 to the negative 3 square, and I should get 49.9 milliamps. Milli means that it's going to be 10 to the negative 3 amps. So just write it as a milliamps. All right, so that's basically the current value. Okay. So, well, let's go back. Part D was asking what is the drift speed of the conduction electrons. So then if I go and look at the drift speed, if you remember, right, so there are several ways I can find the drift speed. There's one with current equation, and there's one with the current density equation. It doesn't really matter which one you use. Remember, so there's a current is equals to Q VD N times the area, or J, which is just NQVD. Well, since I have both of them, it's probably easier just to use from the current density. So I can just say VD is equals to then current density over N times Q. All right. So now let's see. I have current density. I have Q, right? So it's electron. But then what is then N? What is this, this density number, right? This concentration number. Well, from here, what we can do is this. Right. So the N, remember, was number of molecules per unit volume. So let's assume that we have Avogadro number of molecules. So 6.02 times 10 to the 23 molecules. Then, which is basically 1 mole, right? So we're given like 1 mole. And then we have volume. So this V is actually volume again. So then how do we find volume? Well, remember, we are technically given that there is 1 electron per atom. That means we can assume that if you have aluminum, atom, then you can find the volume from this equation of, remember, density is mass per volume. So then this is the density, which is mass per volume. So then the volume is, mass times density. Sorry, volume here is mass over density. In this case, the rho is the density, not the resistivity. That means I can say that volume here is basically replaced with mass over density. Mass is 26.98 grams for each, the aluminum atom. Then this is divided by, so let's say this is divided by the density in grams. So then we can just cancel the grams. So 2.7 times 10 to the 6 gram per cubic meters. Okay. That means if we use this, I can calculate N to be 6.02 times 10 to the 28 electrons per cubic meters. Okay, that's, finding N. Then I can calculate VD, which is J, which was 6.35 times 10 to the 6 amps per square meters, divided by N, which is 6.02 times 10 to the 28, electrons per cubic meters. And then this will cancel with that. So then you basically get 1 per second. So VD is equals to 659 times 10 to the negative 6 meters per second, or 659 micrometer per second. You can see, right, drift velocity is very low whenever you're considering, electrons moving in some kind of conducting wire. All right, so this was part D. Part E, if we go back, it says, what potential difference must exist between the ends of a 2 meter long length of the wire to produce the stated electric field? All right, so easy enough, because we're given electric field, we're given the length, just V is equals to E times L. So since we are told it's fairly uniform electric field, so I can just use this equation, 0.2 volts per meters times 2 meters, meters cancel out, and we get zero 0.4 volts. Relatively low amount of potential difference. All right, so this is basically the last part of this example. Here's one more. If the magnitude of the drift velocity of free electrons in a copper wire is 7.84 times 10 to the negative 4 meter per second, what is the electric field in the conductor? All right, so what we do from here is looking at the equation. All right, so in this example, what we can do here is sort of like look at different ways that we can represent, for example, drift speed. So let's say here's the drift velocity. So one thing we have here is there's this equation, right? Kinematic equation, V final equals V initial plus acceleration times time. Okay, so now acceleration is due to the force over mass, and force here is electron times electric field over mass. So then this will be final speed equals initial speed plus the acceleration replaced with electric charge times electric field over the mass times time. Okay. So basically we can have something like this. So in a way, this can, let's say, assuming that, let's say uh, for example, kind of average it out, and let's say if the initial is zero, so then drift speed, which is more or less, let's say, constant, is E times electric field over mass times T. Well, then instead of T, we can use what we call sort of like a tau, which is kind of like a same time, but represents the average time interval between successive collisions. So just representing like, a little bit differently, because it's a exactly average time interval between collisions. So that's why this is sort of like average, the drift velocity and average time between the collisions. All right, so now what we have here is, then I can represent then the current, which was N E VD times A, where I replace VD with that. So it becomes N times E square times the electric field over the mass, then this time times the area. The idea here is that we are relating this drift velocity, let's say, to the electric, to the electric field, because we are given the drift velocity and we want to find the electric field in the conductor. Okay. So let's say find a way to do that. So now I also have then, the current in the previous example, I showed you that it's equals to uh, the, also related to the electric field, so which is electric field A over rho. So rearranging this, then we can get rho is equals to m mass of the electron times n electric charge squared times this the time. And then from here we can rearrange, then this time is equals to mass over resistivity times n times E squared. All right, so the idea is that we have this, and then Vd is equals to, coming back to this equation over there, so it will be E charge times electric field over mass, and replacing this with quantity of m over resistivity and E squared, then we can just have E over resistivity and times electric charge. That means from here we can just set this equation where electric field is equals to rho n E times Vd. So simple relationship that electric field has to the drift velocity or drift speed. Again, so in this equation, E is equals to, say, rho is easy, it's just something that we get from the table. The E is the charge, Vd is given to us. The only thing we're not given right now is the N, which is that concentration number. And to find that, we basically use the same thing as we did before, which is the number of molecules per volume, where then we replace volume with mass times density, mass over density. So it becomes number of molecules times density, let's say density of copper, divided by the mass of the copper. So again, this is the density, where this rho over here is the resistivity. So two different things. But in any way, so let's say 6.02 times 10 to the 23 times 8920. That's the density of copper, kilogram per cubic meter, divided by the mass of the, a copper atom, right, which is 0.635 kilogram per mole. So we can find N to be 8.46 times 10 to the 28 per cubic meters. Then come back and solve for that. So resistivity, 1.7 times 10 to the negative 8 ohms times meters, then times concentration number, 8.4 times 10 to the 28 per cubic meters, then times electric charge, 1.6 times 10 to the negative 19 coulomb, then the drift speed, 7.84 times 10 to the negative 4 meters per second. And all together, we're going to give us 0.184, 0.18 volts per meters. So that will be then the electric field. All right, so next what we can do here is, this is now a simple circuit where we have a battery connected to a resistor. And once its connection, established, there's then the current going from positive terminal coming back to the negative terminal. So then the current goes to the resistor. So then what happens here is there's an energy that is given to those charge carriers from the battery and then go around in the circuit, and that energy is basically dissipated as they go through the resistor. Okay, because resistor, there's a lot more let's say particles, there's a lot more collision, and that energy, some of the potential energy, converted to heat thermal energy. So then we can look at in terms of the rate at which that energy is dissipated, du dt, where then we have ddt, where we take q times delta v for the energy and take the derivative of that. So d dt becomes like, let's say, dq dt. So dq dt times delta v, because delta v is more or less constant, right? Because it represents established potential difference between the conductors, end of the conductors. So then you end up with I times delta v. Du dt, if you remember, is then the power. That means the power is equals to I times delta v. That's the equation for the rate at which the energy is dissipated or provided to the circuit. So power is the rate, given in terms of watts, right? So it's the rate at which energy is delivered to the resistor, or the rate at which energy is dissipated by the resistor. So the units are watts. And we can technically then rearrange this, because V is equals to I times R, rearrange and have three different equations for that. So I times delta V, or I squared times R, or delta V squared over R, depending on which version of those we're using. That means just like the energy for the capacitor, right? There you can do it in terms of QV or VC or QC. Same thing is here. There are a number of ways we can represent that. All right, so let's look at then this example here. So residential building codes typically require the use of 12 gauge copper wire, which 12 gauge basically represents very specific type of diameter. There it is, for wiring receptacles. Such circuits carry currents as large as 20 amps. If a wire of smaller diameter with a higher gauge number carried that much current, the wire would rise to a high temperature and cause fire. That's basically what I already kind of talked about. Calculate the rate at which internal energy is produced in 1 meter of 12 gauge copper wire carrying 20 amps. All right, so let's do that and see what we get. All right, so we're given geometry of the resistor. So we can then say, all right, resistance equals resistivity times length over area. Well, we can solve for this because we are given all the values, right? I know what type of wire it is. It's a copper. So it has a resistivity of 1.7 times 10 to the negative 8 ohms times meters. And then I'm also given in terms of, let's say, length. So we're given length, which is 1 meters. And then what I can do here is I can say that pi times r square, which is the diameter. So basically half of 0.208, right? So 0.205 times 10 to the negative 2 meters, because it's in centimeters, divided by 2 square. And I can then find the resistance, 5.2 times 10 to the negative 3 ohms. That's the resistance for the part A. Part B, it says, what if, repeat the calculation for 12 gauge aluminum wire. Okay, so we did, let's see. So we did aluminum wire, a copper wire first. Now we're gonna do the same thing for the aluminum wire. That means the same equation. The only thing here is it's aluminum rather than copper. And it has a different, let's say, resistivity. So 2 times 10 to the negative 8 ohms times meters, same 1 meter, same pi times 0.205 times 10 to the negative t over 2 squared. So basically in terms of that. And we're going to get then 8.5 times 10 to the negative 3 ohms. So that's the resistance for this wire. Okay. The last one says, Don, explain whether 12 gauge aluminum wire would be as safe as the copper wire. Okay, so what we can see here is, so one way we can do here is to find the amount of power. So power for the copper wire is basically current times voltage, for example, or current squared times resistance. So since I have the current 20 amps and, let's say do the resistance. So 20 amps squared times 5.2 times 10 to the negative 3 ohms. So I get 2.1 watts. If I do the same thing for the aluminum, then I'm going to get 20 amps squared, then times 8.54 times 10 to the negative 3 ohms. So I get 3.42 watts, which means I get a little 1.5 times more power output. That means like it dissipates much more energy than, let's say copper. So aluminum basically like almost 50% more energy dissipated, which means 50 times 50% more, energy converted to heat, which can make it much hotter. And so probably not very useful. Maybe insulating that wire will make the difference and it will make it, let's say, more safe. But at this point, probably, using a copper wire is a safer bet.